All right, welcome back. So we looked at a couple days of systems, and then yesterday, well, I don't know if you're going daily here, but the last lesson was a look at some matrices, and now I want to tie the two of them together. So we're going to look at matrices to solve systems, and then we're going to look at something called determinants to solve systems. And honestly, matrices are one of the more complicated way to solve a system, especially if it's a 2x2 or 3x3, because using our calculator, Desmos, or even solving with substitution or elimination is really manageable by hand. So I'm going to introduce you to the concept of solving systems with matrices, but understand this isn't the most efficient way to solve the smaller systems. It's really beneficial when you're looking at larger systems, where probably not until you take maybe a linear algebra, some farther ahead math class that you probably wouldn't see it, but a system of, let's say, 5 equations, 5 variables, then this process definitely outweighs the other processes. Anyway, it's basically elimination, but it handles the process using only the coefficients and constants of your system instead of including those variables. So if we're going to fit a system, first of all, into a matrix, we're going to basically eliminate the variables. So we're going to put the coefficients of the variables, and we're going to put the constants that are on the other side of the equal sign into a matrix, and we just eliminate the variables. Don't put the variables in, understanding that the coefficients we put in are still coefficients, okay? And we're going to separate those coefficients and constants by a vertical line. So as you can see with our example here, if I took this system and put it into a matrix, which you could use the giant parentheses, or you could also use brackets. That tends to be what I use when I write these. But either way is fine. You take the coefficient of 1, and then the 2, and then the 4, right? 1, 2, 4, and then we have our constant of 4 here. We've got 3, -1, -1, 3, -1, -1, and then our constant of 10. Or 5, -3, 1, 5, -3, 1, and then our constant of 1. Okay? So if we're going to put a system into a matrix, that's how it looks, and we call this the augmented matrix. So the augmented matrix is the coefficients and constants from a system, and the goal is to use a series of row operations that we'll talk about in a little bit to get this matrix into what we call upper triangular form. Upper triangular form. Okay, let me try that again. Upper triangular. Okay, so upper triangular form. If you notice the matrix here, we've got zeros forming a triangle here, but we have this triangle of coefficients that still exist. This is what we call upper triangular form, so it's like the upper triangular part of the matrix. It's the only place where we have values. Since these are zeroed out, we actually can use back substitution to solve from this point. So there are 3 rules that we can use to manipulate any matrix, and again, I'm going to show you those in a little bit, but the goal is to get the matrix to look like this one, because once we're here, we have the first part of our solution. So this says 0 x's, 0 y's, and 1 z have to equal 3. So z has to equal 3 is what that last thing says. And then I could take it and substitute back in. So the next level there says 0 x's, 1 y, and 2 z's have to equal 7. Well, we just figured from the previous step that z was 3. So that 2 times 3 is 6, and if I subtract that 6 over, that means y has to equal 1. And now I have 3 and 1 for y and z, which means I can plug both of those back into the first equation. So I have 1x plus 3y minus 5z that has to equal 8. Well, y we said was 1, and z we said was 3. So if we take the 3, subtract the 15, that's going to give us a minus 12. And if we add that minus 12 over, then we see x has to equal 20. So if we can get our matrix to look like this, it basically means get our system to look like this, right? We essentially have it solved for z, and we use back substitution. And then our solution would be 20 and 1 and 3. Okay, so from there, it's really the elimination and back substitution process we've already seen. Now, if we use those same operations that we'll talk about in shortly here to manipulate the matrix completely, a completely solved matrix would look like this, where we have 1x, 1y, 1z completely solved for, right? 1x would have to equal 5. So this first row here says x equals 5. The second row here says y equals -3. And this last row says that 1z equals 2. So that's how it would look if it was completely solved, okay? And this is what we call reduced row echelon form. That is really fancy language. The only reason I mention it is because this process is something that can be worked with the calculator. When your calculator solves a system of 3 by 3, or a 3 by 3 system of 3 equations, 3 variables, it uses matrices to do it. And if you're using a TI specifically, in the final step of solving, you have to push this button that says RREF. That's basically asking your calculator to put it in reduced row echelon form. That means that's how the calculator, that's the language the calculator uses to say, hey, solve this system, okay? So I'm not so concerned that you know that language. Just know that when you're pushing that RREF button, you're telling your calculator to solve a matrix, okay? You're trying to get it to look like that. All right, so now let's talk about these rules. What are we actually doing to manipulate a matrix? So there are 3 rules, and I'm going to hopefully help you understand when we're going to be using each of these rules. And really, the rules are the same rules we use for elimination, okay? One of the rules is that any rows can be rearranged or interchanged. Rows can be interchanged. So I can just take the first equation and write it second, and take the second equation and write it first. Or in a matrix, I can take the first row and write it second, or take the second row and write it first. I can just move rows around. As long as all the coefficients and constants move together, it'd be the same thing as just swapping equations around, okay? Now, if we're going to use that, it won't be used often. That step would always be used that rule would always be used in a first step, okay? And then we can also multiply rows by any non-zero number, right? Like we were using with elimination. If I wanted to take this whole equation and multiply it by 2, that's a legal move. Well, that's also a legal move in matrix operations. So rows can be multiplied by any non-zero number. And we can also multiply by fractional amounts, which is like dividing a whole row by 4. Multiplying by a fourth would be the same thing. And then the last one is the one that seems tricky, but again, it's elimination. You can change a row by adding to it a multiple of another row. So again, if I was just using elimination here, let's say I wanted to eliminate the y's. If I multiply this whole equation by a -2, it gives me a -2x, a -2y, and a -8. Well, then I could add these 2 rows together, and I get a new equation. I get 3x equals 3 here. Okay, so it's the same concept with matrices. I can multiply a row by a number, and then I can add it to another row to get a new row, all right, where the y's zero out here. So same rules we use in elimination, just looks a little weird when we're dealing with the rule in a matrix and we've taken the variables away, okay? So the goal is one of 2 things. If we're looking at a 2 by 2 system, our 2 by 2 goal is to get that upper triangular form. If it's 2 by 2, we want a 1 here and a 0 here, and then it doesn't really matter what number is here, but we need a 1 here. So the goal is to get the 1 and the 0 and the 1. And then if it's a 3 by 3, our 3 by 3 goal is to get a 1, a 0, a 0, a 1, a 0, and a 1. And then it doesn't matter what numbers are here. Okay, it's those zeros and ones that we've got to get. It's that upper triangular form, because then I have my first part of my solution here and here. And to get those goals, we begin in column 1, and then we work down, and then we'll go to column 2 and work down, and then we'll go to column 3 and work down. And once the matrix is in that correct form, we use back substitution, like we saw a few minutes ago. Okay? So bear with me here. Again, not the most efficient way to solve. You could absolutely just solve this algebraically by hand, or absolutely put it in Desmos and get to the solution. And I would probably do that first here just to know what I'm working toward. But this is a helpful skill if you move on to later math, and it's good exposure for you because you will be moving along. Okay? So first we want to put this in what we call the augmented matrix. So in a matrix, in a matrix, we remove the variables. So we've got 5, 2, and then our equal sign sort of gets replaced with this vertical line. Then we have our 11 here. Then I have 1x, 1y, and 4. So this is our augmented matrix. And the goal, remember, is to get a 1 here, a 0 here, and then a 1 here in that order. So it's the 1, and then the 0, and then the 1. Well, the first rule says, well, I can just swap these rows around. So all I'm going to do for my first step here is just rearrange these, because I got a 1 here and I need it to be here. So I'm just going to swap row 1 and 2. So row 2 and row 1, I'm just going to swap. And I'm going to try to show my row operations on the side here just so I don't get lost with my work. So I'm just swapping row 1 and row 2. So 1 and 4 go here. And 5 and 2 and 11 go here. Okay, so this first rule that we wrote down where rows can be interchanged, you're really only going to use that in the first step. After the first step, you will probably never use that rule again, okay? All right, so now that we're here, we've got the 1, we've got the first part of the goal, now we need the 0. And to get a 0 is where we use the third rule. So this third rule, this is the one we're going to use to get zeros. Okay, so if I need a 0, where I have a 5 right here, what would I have to add to 5 to get 0? Well, I'd have to add -5. And I get the -5 by multiplying another row and adding it. So if I took row 1, for example, and multiplied it by -5, -5 times row 1, okay, let me just show you here. -5 times row 1 would give me a -5 there, and that -5 and that +5 would give me the 0 that I need. So what I'm going to do to get my 0 is, try not to destroy my paper here, is I'm going to take -5, multiply it by row 1, and add that to row 2 to get my new row 2. Okay? So I have -5 times row 1. If I multiply -5, -5, -5 by each of those numbers, -5 times 1 is -5. -5 times 1 is -5, and -5 times 4 is -20. If I add that to row 2 was 5, 2, and 11. What I'm going to get is a new row 2. That's 0, -3, and -9. So that's my new row 2. So now I can rewrite this matrix as 1, 1, 4. So I wasn't trying to manipulate row 1, I was trying to manipulate row 2. So all I changed is row 2, which is now 0, -3, and -9. Okay, so I'm one step closer to the goal. The goal was to get the 1 here, the 0 here, and then lastly, this 1. So I can do that using my second rule. The second rule here is the one I'm going to use. This is the rule I'm going to use to get 1s. Okay, to get, I guess I should write that out. 1s. So if I can multiply something here to get a 1, that's what I'm going to do. And actually, it's easier to think about it as dividing. If I divided -3 by -3, I get a +1. So I'm going to take row 2 and multiply it by a -1/3. -1/3 times row 2. So row 1's not changing. It's still 1, 1, and 4. But row 2 is now getting multiplied by a -1/3. Well, -1/3 times 0 is still 0. -1/3 times -3 is +1. And -1/3 times -9 is +3. And now we're good, right? This is the first part of the solution. Right here, I know that y has to equal 3. And if I plug that back into any form here, but let's say I go back to my very second equation, right? This second equation right here, x plus y has to equal 4. So if x plus y has to equal 4, right, if x plus y has to equal 4, and we just found that y was 3, then x plus 3 has to equal 4. It tells me x has to equal 1. So my solution, using these crazy matrices, is x is 1 and y is 3. Okay, absolutely not the easiest or most efficient process. I kind of like it. Of course, that's the nerd in me. If you're dealing with larger systems, it's really nice to be able to do this without the variables involved. But ultimately, you're going to have the choice on how you solve. And really, this process is for exposure, okay? So don't freak out too much. It's good practice for you, but if you don't end up nailing this, don't freak out. It's just for exposure, just so you see it, okay? So I'm going to try to show it to you again. All right, so I'm going to put this into an augmented matrix. So in matrix form, we're looking at 4, -3, and 5, 7, 2, and 16, okay? So the goal was to get the 1, and then the 0, and then the 1. So I need to get a 1 in this first spot. Now to get 1s, it's multiplying or dividing a row. So I'm just going to take my first row. If I just take this and divide by 4, I'm going to get that 1. So I'm going to do 1/4 of row 1. So I'm not changing row 2, okay? I'm just dividing everything in row 1 by 4. So 4 divided by 4 is 1. This is going to be -3/4 here. It's not the best, but it happens. And then 5 divided by 4 here is going to be 5/4 here. Okay? So I got the 1. And now my next goal is to get a 0. So to get this to be a 0, I have to use that third rule. I'm going to take -7 times 1 and add it to the +7 that I have here. So -7 times row 1 gets added to row 2 to change my row 2. Okay? So -7 times row 1. If I multiply -7 by each of these, that's going to give me a -7. -7 times -3/4 is going to be +21/4. And then -7 times 5/4 is going to be -35/4. I'm adding that to 7, 2, and 16. So these give me the 0. That was the goal. Not going to lie, I'm going to use my calculator here to add these fractions. So 21/4, I just don't want to make a silly mistake. 21/4, and then we're going to add, good grief, we're going to add 2 to that. That's going to give me 29/4 here. And then -35/4. And I'm going to add 16 to that is going to give me 29/4 again. So this is going to be 29/4 again. Okay, so that's giving me a new row 2. Remember, that was to get the 0 right there. So row 1 didn't change. 1, -3/4, and 5/4. And then here, I've got now my 0, 29/4, and 29/4. Now, hopefully you can see at this step what's happening here, but if we wanted to just practice using our row operations, my last part of the goal would be to get the 1. Well, if I multiplied by the reciprocal of 29/4, if I multiplied by 4 29ths, my row 2, then again, row 1 wouldn't change. I'd still have 1, -3/4, and 5/4. But row 2, well, 0 times 4 29ths is still 0. But if I multiply here, I get a 1, and here I get a 1. And that shows me the first part of my answer, so I know y has to equal 1. And now, it doesn't matter what you plug into. I'm just going to use my first equation. First one says 4x minus 3y has to equal 5. So 4x minus 3 times 1 is 3 has to equal 5. That means 4x has to equal 8, and x has to equal 2. So I have a solution of 2 and 1 on this matrix. Okay? I know, not the best, but manageable, and if you did it enough times, maybe you'd come to like it as well. In the interest of time, I'm going to go ahead and skip number 3 here. I just, again, want you to see this because it's good exposure for you, but honestly, I don't care how you solve as long as you can get to the answer, so hopefully you're comfortable with one of the other methods. And then I put one of these on your assignment. By all means, use whatever method you want to solve. I would like for you on the 2x2 on your practice to try this one out, but it's a bit much, okay? So we're going to go ahead and skip number 3, and now I'm going to show you another way to solve systems. So we have substitution, elimination, graphing via Desmos, matrices, which I would probably avoid, especially for these smaller ones. And this last method I'm going to show you involves what we call determinants. So the determinant of a matrix, this method is not so bad. It's a little obscure. Again, going to be more useful later in math, but the determinant is the difference of the cross products. The difference of the cross products. So if you cross multiply and subtract, in this case cross multiply A times D and B times C, and then subtract those results. In my head, let me just show you how this wraps around in my head. So you're starting here, and then, oops, did that backwards. You're starting here, and then you're going here, okay? So A times D minus B times C. If you did that for a system or matrix, you're going to get what we call its determinant, okay? And let's just evaluate that a couple of times. So if you did 3 times negative 2 minus 1 times 6, 3 times negative 2 minus 1 times 6, those cross products, the difference of those cross products here would be negative 6 minus 6 would be a negative 12. We would say this determinant is negative 12, okay? Or here, 4 times 2 minus 5 times negative 1, 4 times 2 minus 5 times negative 1 is going to give us 8 and then plus 5. So we'd say the determinant here is 13. Okay? Now again, if we put this in terms of a system, Gabriel Kramer developed a way to use these determinants to solve. So we have the determinant of a 2 by 2 system. Now, determinants can be used for larger systems. We're just going to focus on 2 by 2s. We have the determinant for the coefficient part of the system, so just the A, B, C, and D. We're going to call that just the determinant for our matrix. If you want the determinant of the x values, then you actually put in the constants in the x spots here. And if you want the determinant of the y's, you're going to put the constants in the y spot, okay? Seems a little confusing, but as long as our original determinant, D, isn't 0, we can use each of the determinants to find our solution to our system. So let me show you. So we want to make sure our determinant isn't equal to 0. So the determinant of the 3, 6, negative 2, and 1, that determinant, okay, is going to be 3 times 1 minus negative 2 times 6. So 3 times 1 is 3. Negative 2 times 6 is negative 12, but if we subtract a negative 12, we're going to add the 12, so we get 15. So our determinant is 15. Now, in order to find our solution, we need to also find the determinant of x values and determinant of y values. So for the determinant of the x values, in the first column here, we put our constants, so the 4 and the 13. And in the second column, we leave our y coefficients, the negative 2 and 1. So now it's 4 times 1 and minus negative 2 times 13. So that's going to be 4 plus 26, which is 30. And the determinant of our y values, we leave the x's this time, the 3 and the 6, and we put the constants in the y column. So the 4 and the 13 go here. And if we cross multiply 3 and 13, we get 39. Let me just do the work here. Subtract the 4 and 6. So this is going to be 39 minus 24, which is 15. Okay? Now, according to Kramer's rule, let's see if I can squish this in a little bit better. According to Kramer's rule, if we take dx, our solution, is going to be at the, where'd I go? Sorry. Our solution is going to be the determinant of x over the determinant and the determinant of y over the determinant. So in this case, the determinant of x we found was 30, and the determinant of the whole thing was 15, and determinant of y was 15, determinant of the whole thing was 15. So the solution is going to be at 2 and 1. All right, now that might be a little bit complicated. If you watch it a couple more times, maybe you'll follow what I did. I think substitution elimination probably still easier than this particular method, but again, this is for exposure, and just so you can see it. And if you like it, you can use it, but you're not restricted, right? You can use really whatever method you're comfortable with. So let me just run through one more here. This next guy, our determinant for this whole thing is going to be the 5, or for our coefficient, this is the coefficients, we don't use the constants for the determinant of the system. So 5, 2, negative 1, and 3. That's 5 times 3 minus negative 1 times 2. So 15 plus 2, which is 17. the determinant for x's. We put the constants in the x column here. Oops, not a fraction. So the 13 and 12 go in, and we leave the coefficients of y, 1 and 3. So 13 times 3 minus negative 1 times 12. So that's going to be 39 plus 12, which is going to be, I can't add, 51. Determinant for y. Okay, we're going to leave the x's here. So 5 and 2, we put the constants in for the y column this time. So 13 and 12. And so that's 5 times 12 minus 13 times 2. So that's 60 minus 26. And that's going to give me 34. Okay, so the solution, according to Kramer's rule, is going to be dx over d, dy over d. So in this case, what do we got? 51 over 17 and 34 over 17. And that ends up being 3 and 2. So the solution is at 3 and 2. Okay? Again, I know I ran through that pretty quickly. This is, again, for exposure. If you like this method, I do. And I showed a lot more work than if I was actually doing this myself. Probably whip through some of those things a little faster. But if you want to try this out, it doesn't hurt to practice the process. But ultimately, when it comes down to it, you can use whatever method you want for solving. Now, I skipped number 3 here. If you want to see that worked out, I'd be happy to work it out for you and send you a picture. Just email me. Again, all this is for exposure and give you some other options for solving, although you can use whatever options you're comfortable with. Okay? Email me if you have questions. Again, email me if you want to see number 3. And